You know that moment when your phone just unlocks by looking at your face? Or when you can scribble a note and your tablet somehow reads it? It feels like magic, right? Well, today we're pulling back the curtain on that magic. We're talking about neural networks, and we're going to break it all down, from the squishy stuff in our heads that started it all right down to the actual code. Seriously, think about it for a second. How on earth can a computer look at your specific, kind of messy handwriting, a style it has never ever seen before, and just read it? How does it do that? It's not magic, but you know what? The answer is inspired by something that's maybe even more amazing. Yep, you guessed it, the human brain. Turns out, to build a machine that can learn, the smartest people in the room decided to look at the best learning machine we know of, the one right between our ears. So, let's get into it. This whole idea isn't some newfangled thing from the last few years. Nope, we're talking way back in the 1940s. You had these brilliant pioneers looking at how our brains work. You know, all those neurons firing and connecting. And they had this wild idea. What if we could build a math version of a neuron? A blueprint for thinking, but inside a machine. And this is the key right here. On the left, a real biological neuron. It gets signals, chews on them, and decides, yep, I'm firing, or nope, staying quiet. On the right, the artificial version. We just call it a unit. It does the exact same thing, but its world is all numbers. It gets numbers in, does a little bit of math, and spits a number out. That's it. It's the fundamental building block for everything else. Okay, so here's where it gets really cool. Think of that single artificial neuron as one Lego block. By itself, it's just a block. It's simple. But what happens when you snap thousands or millions of these Lego blocks together? You can build anything, and that's the whole secret. The mind-blowing part is that nobody programs the intelligence. It just emerges from connecting a ton of these really simple little calculators. All right, let's zoom in on one of these Lego blocks. So a bunch of numbers come in as inputs. Each one gets multiplied by something called a weight. Just think of a weight like a volume knob. It turns some inputs up because they're important and turns others down because they're not. Then all those adjusted numbers get added together. We also add one little extra number called a bias, which kind of nudges the final result one way or another. And that final sum, it gets sent to one last decision maker. And that final decision maker is called the activation function. I like to think of it as a bouncer at a club. It looks at the final number and decides if it's high enough to get in. Is it past the threshold? Cool, you're a 1. The signal passes. Nope, not high enough? You're a 0. The signal stops here. It's a simple yes or no gate. Okay, let's make this real. Let's see how one of these neurons can learn a basic logic rule, like OR. So our inputs are 1 and 0. First, we multiply each by its weight, which we've set to 1. That gives us 1 and 0. Simple enough. Then we add them up, which is 1, and we add in our bias, which is -1. So 1 plus -1 gives us a final sum of 0. Now, the activation function, our bouncer, looks at that 0. The rule is, if the number is 0 or higher, it says yes. So it outputs a 1, which means true. And boom! The neuron just correctly figured out that 1 or 0 is true. It's just basic arithmetic, but this is it. This is the seed of machine intelligence. Okay, so for a simple logic gate, we can just figure out the right weights and biases ourselves. No big deal. But what about teaching a network to know what a cat looks like? A cat can be fluffy, skinny, sleeping, jumping. There are millions of pixels. There's no way we could set all those millions of volume knobs by hand. So the network has to figure it out for itself. It has to learn. And that is the billion-dollar question in machine learning, isn't it? How do you go from a network that's basically just guessing randomly to a finely tuned machine that can make incredibly accurate predictions? How does the learning actually happen? Well, the answer is a really clever idea called gradient descent. Here's the best way to think about it. Imagine you're standing on a huge, hilly landscape, but it's completely covered in thick fog. Your goal is to get to the lowest point, the bottom of the valley. You can't see it, but you can feel the ground beneath your feet. So what do? You feel around for whichever direction is sloping down the most, and you take a small step. Then you do it again. In this analogy, the height of the hill is how wrong the network is. We call that loss. Gradient descent is just the process of feeling for that steepest downhill direction and nudging all the weights a tiny bit to get less wrong. So it becomes this really simple but powerful loop. Step 1, start with totally random weights. Just guess. Step 2, feed it some data and see how badly it messes up. That's your loss. Step 3, figure out which way is downhill to make that loss a little bit smaller. Step 4, adjust all the weights just a tiny bit in that direction. And then you just repeat that over and over and over.
thousands, maybe millions of times. With every single cycle, the network gets a little bit smarter, slowly rolling down that hill towards the right answer.
Okay, so we've got a learning mechanism. Awesome. But a network with just one layer of these neurons is, well, it's a bit basic. It's like trying to solve every problem by just drawing a single straight line. And let's be honest, the real world is way more complicated than that. To tackle something messy like computer vision, we can't just go wide. We have to go deep.
And going deep just means we stack more layers of these neurons between the input and the final output. These middle layers are called hidden layers, and they are the secret sauce. Think about it. That first layer of neurons can learn a bunch of simple straight lines, but the next layer doesn't see the original data. It sees the lines from the first layer, so it can learn to combine those simple lines into more complex shapes like curves and corners. And the layer after that combines those shapes into even more complex patterns. This is how a network goes from seeing simple lines to recognizing a face.
Now, for images specifically, there's a special type of deep network called a convolutional neural network, or CNN, and it has this one brilliant trick up its sleeve called convolution. Imagine you have a tiny little feature detector, like a little magnifying glass that's built to spot only one thing, say a vertical edge. Now you slide that little detector across every single part of the image. Everywhere it finds a vertical edge, it lights up. The network actually learns dozens of these little filters, one for vertical lines, one for curves, one for a specific texture, and scans the image with all of them to create a map of all the interesting features. Okay, so after running all those filters, you have a ton of information, all these maps showing where the edges and curves are. It's too much data, so the network does something called pooling. It's basically just summarizing. It takes a small section of the feature map, say a 2x2 square, and just keeps the most important signal from that area, throwing away the rest. This does two amazing things. It makes the whole process way faster, and it also makes the network better at spotting an object even if it's a little bit off-center or rotated.
All right, that's enough theory. It's time to see how the rubber meets the road. How does all this abstract talk about layers and filters actually turn into code? Let's look at some real examples using a super popular tool called TensorFlow. You might be surprised how straightforward it is. Check this out. This is real code to build a network that can spot fake money. See that model.add line? That's literally us adding a new layer of neurons. The first one adds a hidden layer with 8 units, and that activation equals ReLU part, that's just a modern, super efficient version of the bouncer function we talked about. The second model.add line creates our final output layer, just one neuron that spits out a single number between 0 and 1, telling us the probability that the banknote is a fake. All that theory we just discussed, it boils down to these 2 lines of code. It's amazing.
So you run this super simple code, you train it on data, and what happens? How well does it do? It hits 99.8% accuracy. Let that sink in. A couple lines of code, and it can spot a fake with near-perfect precision. That is the raw power of this stuff.
Okay, now for the grand finale, the handwriting recognizer. Look at this code. You can literally see the concepts we just learned. There's conv2D, that's our convolutional layer, the little filters scanning for features. And right below it, max pooling 2D. That's our pooling layer, summarizing the results. It's not some hidden complex thing. The ideas translate directly into the code you write.
And the result, for this more complex problem with all the messy, loopy, weird ways people write numbers, how'd it do? 98.8% accuracy. It just learned how to read. That's what's happening here. It's pretty incredible.
So think about the journey we've just been on. We went from a single brain cell to a single artificial neuron to these deep networks that can actually see. But for all their power, these networks have a kind of amnesia. They only know what they're looking at right now. They have no concept of the past.
So what's the next step? Giving them memory. That's where things like recurrent neural networks, or RNNs, come in. They're built with a special loop that lets them remember what they just saw. And that's the key to understanding things that happen in a sequence. It's how AI can translate a full sentence, not just word by word. It's how it can understand a video, not just a single picture. It's about moving from seeing a snapshot to understanding a whole story.
You know, we kicked this all off with a pretty simple question about handwriting, and now we're talking about networks that can understand language and video. What we've seen is that the basic idea, that little Lego block inspired by our own brain, is actually not that complicated. But when you connect millions of them together and give them a way to learn, their potential is just staggering. It really makes you wonder, right?